Okay, so our goal is going to be to compute the pH along titration curves. Now, this is not overly difficult, okay? It's going to follow an organized approach that we're really always going to follow. And believe it or not, we've seen this. It's essentially going to be an RICF table. Maybe sometimes we're going to do an ICE table. More or less, the mechanism for solving these problems going to be very, very similar, okay? Once we get a feel for it. Now, the thing is that each individual type of titration curve gets handled in a slightly different way. And we're going to have to kind of develop a chemical intuition to help us out. Now, the first question that you have to answer is this one. When you're faced with the problem, you want to compute points along the titration curve, you have to know, is this a strong acid, strong base titration? Is this a weak acid with a strong base? What are the characteristics, the chemical characteristics of the acid and the base that I'm titrating? You have to figure that out first. And that's why memorizing that list of strong acids and bases are so crucial. If you can memorize that list, if you're dealing with components on that list, strong acids and bases, you handle it one way. If you're dealing with weak acids and bases, you do it a little bit differently, okay? Now, after you do that, you're going to make an inventory of the acid and base present, and you're going to try to convert to moles whenever possible. We're simply going to do an RICF type inventory approach, figure out what's in excess, what's been consumed, where we're at on this titration curve. So that's actually part number 2 here. Determine which region of the titration curve you're working. We're going to figure that out through an RICF approach. This is going to allow us to predict what controls the pH and solve for the pH, okay? That's going to involve writing out a chemical reaction or equation, making an inventory of what's present. Again, I want to rehash that while this may seem complicated in some cases, and sometimes students struggle with it, working these problems, it's a little tedious, but it's really not all that difficult. It's just basic mathematical operations and chemical intuition. It's just going to require that you practice a little bit, okay, to solve for the desired information. And I want to impress that upon you. Now, I'm going to go through the different sample types that you might see on the exam. We're going to start with the easiest. This is when we're going to titrate at SA and SB, which is strong acid with a strong base. Both components dissociate completely. To give us an example problem, let's consider the titration of 50 milliliters of 0.0 mole to 0.0 molar KOH, 0.02 molar KOH, gosh, tongue tied today, with 0.1 molar HBr, okay? Now, the first thing I encourage you to do, when you're given information like this, write out your drawing, okay? That explains what's going on. Now, 50 milliliters of 0.02 molar KOH. Sounds like that's our sample down here, right? 0.02 molar KOH, potassium hydroxide. We recognize that as a strong base. Now we're going to titrate that with our titrant, 0.1 molar HBr. And just like HCl, hydrobromic acid, is a strong acid. So this is strong acid, strong base titration. This is the experimental setup, what it would look like. Now, what we want to do here is think about placing pH electrode down in that flask and having it read out in pH units, okay? And we'd want to be able to predict what that pH meter might read at every point along our titration curve, from the point where before we start the titration, before we add any titrant, all the way through equivalence to excess titrant. Now, if we're just thinking about this, we've got this beaker of a strong base down here. If I was to ask you what the pH was down there, you'd probably say it's pretty basic, right? We could even calculate it based on this. We'll do that in a second. So we're probably going to start, if we're thinking about the shape of the titration curve, this is an example of what the titration curve will look like. Let's print it out so we can see it, right? But if we're thinking about this general shape, we're probably going to start off pretty basic, pretty high pH at first. because we got excess base down in that flask, a lot of KOH, right? Now we're going to start adding the HBr, and we're going to titrate or consume that base. Eventually, we'll add enough HBr to reach equivalence. And it turns out that for strong acid, strong base titration, pH is 7 at the equivalence point. Now that has to be strong acid, strong base. That rule changes for other types of titrations. But for strong acid, strong base, the pH is 7 at the equivalence point. It's the steepest point of our titration curve as we're transitioning from very, very, very basic conditions to low pHs, which are very, very, very acidic. And of course, the reason why that occurs is because we run out of the KOH that was in our sample. We add too much acid, we over titrate, we get past the equivalence point, and we've got an excess of acid there, the HBr, because we just added too much, right? So this is what we expect to go from the basic regime down to the acidic regime, and pH 7 is going to be our equivalence point for the strong acid, strong base. But that's all great, and that's kind of our expectation. But it's also, a little bit cartoonish drawing. We'd like to be able to actually explicitly solve for the pHs along this curve, and in doing so, understand what in the world controls the pH at each and every point. Okay, so let's try to do it. Why not? All right, let's see if we can make sense of it. So I want to solve for what the pH is in that receiving flask when 0 milliliter of the titrant is added. I want to solve for what the pH is when 5 milliliter of the titrant is added. I'm going to do it for 10 milliliter. And I'll also solve for 16 milliliter. And of course, the titrant's the HBr. Let's see if we can do this and make sense of it. Okay, so making sense of it's the key. Now I'm going to switch over my whiteboard here so we can work our way through this problem. Now, as I mentioned earlier, there are different regions on the curve, and these points I've chosen are really not chosen arbitrarily, but to show the different regions. And I think we'll see that as we go through this problem. So the first one's 0 milliliters added. This is like basically before the titration starts. It's always the first region, the 0 milliliter point. So you've got to ask yourself, okay, well, what's in my sample flask that I'm measuring the pH of at this point, the 0 point? I want to come up with this titration curve, right? Which is my pH versus the volume of the titrant. But I need a point right here at 0. What's the pH at 0? Well, what's in this flask? If you haven't added any of the acid yet, the HBr, no titrant's been added. What's in that flask is the only thing that's important, right? Well, I've got a strong base. I've got potassium hydroxide. And we know that when we put that into water, it dissociates 100% because it's a strong base, doesn't it? So all of our formulated units of KOH break up into these ions. So if I specify 0.02 molar this, what I'm really saying is I've got 0.02 molar hydroxide and 0.02 molar potassium. And of course, this one directly impacts the pH, doesn't it? And I'm told the concentration of it. So, this is really easy. Look, if I take the negative log of 0.02 mole per liter, which is my concentration of hydroxide, isn't that my pOH? And sure enough, it is. Okay, so this is almost a freebie, right? You just have to take the negative base 10 log of that number, 0.02. And when I did that, I get 1.69897, not paying attention to my pOH, not my pH, but my pOH. But we are well versed enough in acid-base chemistry at this point to recognize pH plus pOH has to equal 14 for our aqueous system at 25 degrees. We're going to run this at 25 degrees, and that will always be the case. So I can easily solve for pH by taking 14 and subtracting that number for pOH. When I do that, I get a pH of 12.3, thereabouts. We'll call it 12.3, okay? So right here, 12.3 is my initial pH. And that's almost a freebie, right? Because it's a strong base, it dissociates completely. I could have put the acid in the flask, the sample flask, but it would have been probably even easier problem because if it's a strong acid, it dissociates completely. Hey, find the concentration of H plus and sulfur pH. This is not a problem for us at this point, or hopefully it's not. We've worked that type of problem before. All right, so now the fun starts. We're going to actually start to titrate things. So we're not interested anymore in 0 milliliters because we successfully solved that one. Now we want 5 milliliters of titrant added. So what that means is I'm going to drain 5 milliliters of my HBr into that flask. What's the new pH? And here's the thing. When I do that, I actually start my reaction, don't I? I mix my HBr with my KOH. Strong acid, strong base, mix salt and water. So water is one product, salt's the other. That's going to be my KBr here, aqueous. All this is aqueous phase chemistry, right? 1 to 1 to 1 to 1 stoichiometry, balanced chemical reaction. Now, if I want to think about this reaction, it's usually pretty quantitative. So I added 5 milliliters, but I don't know if that's enough to reach equivalence point, or maybe I'm before the equivalence point, maybe I'm after the equivalence point at 5 milliliters. I really don't know. But if I do an ICF table, in terms of the number of moles of everything, boy, I can quickly find out where I'm at. That's what I'm going to do. I'm going to assume the reaction goes to completion. And if that's true, this just becomes a limiting reagent problem. So to compute the number of moles of everything present, I'll go back to my good friend molarity times volume. Let's compute the number of moles of KOH. My molarity was 0.02 moles per liter, and my volume, 50 milliliters. Now I'm going to convert that to liters, as is typical, by dividing by 1,000. It's 0.05. So if I take 0.02 times 0.05, I find that I've got 0.001 mole of my KOH. Easy enough. I can do a similar computation, not for KOH, but for the acid, which I add. Now, my HBr titrant is 0.1 mole per liter. And in this case, I'm going to add only 5 milliliters of it. Now, if I convert that to liters, 0.0005. So my number of moles of HBr should be 0.0005 mole. 0.0005 mole. Now these are my initial quantities of my acid and my base, right? Now I mix them together, they react. I already alluded to the fact that we're going to treat this like a limiting reagent problem. We're going to see what we run out of first. And since it's a 1-to-1 stoichiometry between my reactants, it's pretty easy to figure out. It's just whichever one has the lower number of moles present. So to me, it looks like that's the acid. I'm going to run out of that first after half a millimole reacts. Now I have 1 millimole of KOH, half of it's going to react. So I should have half a millimole remaining. And I'll make some water and I'll make some salt. Neither of these affect pH. I don't really have to even worry about how much I make. They don't have any real effect on pH. So once we do my inventory, the picture becomes more clear. I can see where I'm at on my titration curve now. And what I mean by that is that we have to use our chemical intuition now at this point to figure out whether we're at the equivalence point, before the equivalence point, past the equivalence point, and then furthermore, what in the world controls the pH in our solution? Now I said it's not the products. It's certainly not HBr, we're out of that. But I notice that I still have excess sample down there in that flask, don't I? I haven't titrated at all. I added some acid, so I started the titration. But I've not been able to consume all of the KOH which was in that flask. I have excess sample. And I recognize that KOH, potassium hydroxide, is certainly a strong base. Dissociates completely. So I've really got 0.5 millimole of hydroxide ion in solution, just floating around free. And that's certain to affect the pH. And it's going to have a major influence on the pH, right? This 0.0005 mole of hydroxide ion that I just can't titrate. Now, if I could solve for the concentration or the molarity of that OH minus, I'd be in business. And that's what I'm going to do. So I'm going to divide by a volume in liters, a total volume. Now, what is that total volume? Well, I started with 50 milliliters down here in that flask, didn't I? And now I added 5 milliliters of titrant. I'm going to assume that the volumes are additive, which makes 55 milliliters, which is 0.055 liters. So notice here that I'm dividing by my new volume after I've essentially diluted by adding titrant. So I'm going to take my 0.0005, the number of moles of hydroxide that's left, and I'm going to divide that by 0.055, or 55 milliliters expressed in liters. When I do this, I found that my hydroxide concentration in that flask is expected to be 0.00909 moles per liter. That's my expected hydroxide concentration, okay? So it's been reduced some, and that makes a lot of sense, doesn't it, all right? Because I've used some of it, and I've also diluted it a little bit, okay? Now, once I've solved for the molarity of hydroxide that remains down in that flask, it stands to reason that I, again, could compute the pOH by taking the negative log of that number. After all, that is the molarity of hydroxide that I project to be present. So if I take the negative log of the OH, hey, I'm in business. That's my pOH, right? And we did that. And I get a pOH for this point equal to 2.04, which is, okay, so that's my pOH. And if I want pH, I got to do what? 14 minus pOH, right? So if I do 14 minus the 2.04, I get a 11.96. So I'm switching back to my black marker now. So here at 5 milliliters, my pH has gone down a little bit. Can add a new dot there, 11.96. But again, what I did here was what's important, my scheme for solving this problem, because you're always going to do this over and over and over again. You write the reaction, you do your ICF table, and after you do the ICF table, you have to look at this final amount of everything. Use your chemical intuition to figure out what controls the pH, and then solve for pH accordingly. Now, it's easy to figure out what controls the pH in a strong acid-base titration, because you're either going to have excess strong base or excess strong acid. They dissociate completely, so you simply solve for their concentration after doing your inventory, and you can quickly get to your pH. That's why it's the easiest titration to calculate. It's because you have this 100% dissociation. You don't have to think about anything else. Just figure out what's in excess, how many moles you've got, divide by total volume, and you can quickly solve for pH. Let's work the next point, just to, again, drive this home. So in the next point, we're not going to add 5 milliliters, but we're going to add a different volume. We are going to add 10. That's our third point. So we did 0, we did 5, now we need to do 10. So what changes? Well, if I drain a little bit more of my titrant, my number of moles of titrant is certain to change. So let's compute that. What's my number of moles of HBr dispensed? Again, molarity times volume in liters, very familiar at this point. Molarity is 0.1. Our volume in liters is 0.010 milliliters, which yields 0.001 mole. Well, what about my moles of KOH down in this beaker? Has that changed? Well, I'm still titrating 50 milliliters. It's the same sample volume, the same concentration. In fact, that's not changed at all. And the number of moles of sample component will always be the same throughout these calculations. So I don't even have to change that. That's why I didn't erase it, right? But I do need to update the number of moles of HBr, which I've done. So I filled in the initial amounts of everything, the strong acid, strong base titration. Now I need to predict how things change. It looks like I have equimolar quantities of both of these substances. They're going to react completely as much as they can. And sure enough, look what I get. 0 mole, 0 mole. I have run out of my acid. I've run out of my base. I am at the equivalence point, aren't I? And I've justified that through my stoichiometric calculation. Now, all I have in my beaker at this point are these components. I've got some pure water, and I've got some potassium bromide. This is our salt, strong acid, strong base. It has very little effect on pH at all. And all we've got is essentially this water. Now, we know that neutral water has a pH of approximately 7. So at the equivalence point for strong acid, strong base titration, and only for strong acid, strong base titration, is that true. pH 7 at the equivalence point. So I titrated to 10 milliliters. And gosh, now my pH dropped to 7, didn't it? And actually, if I was to fill in the curve just to see that, what it would look like is it would be pretty flat right to here, and then we get a pretty rapid drop, okay? So if I was actually plotting it out, it would look something like this. And there's my pH 7 point, my equivalence point. I might say then that the equivalence volume is 10 milliliters, VEQ, 10 milliliters, okay? And this point at 5 milliliters is actually 1/2 VEQ, or the halfway point, isn't it? So moving on. So we did 0, 5, and 10. We have one more point to consider, and that's at 16 milliliters. So instead of draining 10 milliliters, we're now going to drain 16. It's even more, right? How are things going to change? Well, clearly we added a little bit more titrant. So we're going to pass the equivalence point because 10 was the equivalence point. So we know we're going to be past the EQ. But what's going to be the pH? Well, let's reason our way through it. The thing that's really changed is the number of moles of HBr. The number of moles of sample, that hasn't changed at all. Now, the molarity of the HBr has always been 0.1, but that volume keeps increasing, doesn't it? And now we added 16 milliliters, which is 0.016 liters. So if I do the math, I get 0.0016 mole of HBr that's been added. So 0.016 mole. All right, so I put that number in my ICF table, I update it. The number of moles of KOH remains the same because that's fixed by my sample that I started with, and I haven't changed my sample at all. I just keep adding more titrant from the burette. So how has the situation changed? Well, again, I look at my numbers for the amount of materials and I assume that the reaction goes to completion. It becomes a limiting reagent problem. And in this case, I run out of my KOH after 1 millimole or 0.001 mole has reacted. Now, since it's a 1-to-1 stoichiometry, that is the most amount of HBr that I can consume. And as a consequence, I'm going to have an excess of HBr now. I am past my equivalence point, which is not a big surprise to us, is it? Because we knew 10 milliliters was our equivalence point. But now we know just how many moles past we are. Now, because I know HBr is a strong acid, it dissociates 100%, making H+. So the concentration of HBr in this solution is really the same as the expected H+ concentration or H3O+ concentration. Now, I can compute the concentration by taking the moles excess of HBr and dividing by the total volume at this point. Now, what is that total volume? Well, again, I started with 50 mLs, and I've now added 16 mLs of my titrant. So I'm assuming additive volumes. That makes 66 milliliters, which is 0.066 liters. So if I take 0.0006 and I divide by 0.066, I get 0.00909 mole per liter, H+ or HBr. And that information is very useful because, of course, we know by heart pH is negative log of H+, right? So if I take negative log of that number, 0.00909, that's going to be my pH of the solution here. And that's my last step to solving this particular problem, right? And when I do that, I got 2.04, it looks like, okay? 2.04 is what I'm indicating here. So let's see, 15, 16 is way out here. Gosh, I have this very, very low pH point. And if again, I fill in the curve, it will come way down and then kind of flatten out again, okay? That's what the curve would look like, 16 milliliters. So that is my titration curve for strong acid, strong base. I mean, here we put the base down here, and that's why it started off at a high pH. We put the acid here, but we certainly could reverse the two. I mean, we could put the acid as the sample, the base and the titrant. It's no big deal. The way you solve the problem would be exactly the same. You write the reaction for the neutralization, and you simply go through this very organized inventory taking approach, right? It's like accounting or something. You figure out how many moles of the acid you add, how many moles of the base you've got, figure out your final condition, assuming complete reaction and consumption. In other words, the reaction moves to the right as far as possible. Decide what's present in that sample beaker or flask. And it's always going to be an excess amount of strong acid or strong base, unless you're at the equivalence point. And at the equivalence point, the pH is just 7. But the point being is you figure out whether you have the excess strong acid or the excess strong base, use the number of moles, convert to a molarity, and from there, find your pH. It really is that simple, okay? So strong acid, strong bases are the easiest case. Now, the next video is going to be weak acid, strong base. A little bit different there. The inventory approach is going to be conservative. We're going to do that again, just that we can't treat weak acids like strong acids, okay? And that'll be different. So that's going to be the next video. I think I'm going to show you an example of a weak base, or at least discuss a weak base, strong acid. And then in a subsequent video, we're even going to titrate polyprotic acids and bases. All right, so we're going to be talking a lot about these curves. You'll find some things are conserved, some things are a little bit different. But in each case, we are going to take an inventory and decide logically what's present along our curve, and that's going to drive our decision making, okay? All right, I'm going to let you watch those videos. Hope you're well.